Hello, everyone. Welcome to the second lecture. First time we're going to be getting into technical material today. First, some announcements. Project Zero, talked about it yesterday. Required but not graded. Please do it by Friday. If you're rusty or new to Python, there will be office hours Wednesday and Thursday, 5 to 6 p.m. in 510 Soda. There's an announcement on Piazza about that if you're interested. Math self-diagnostic, another thing we talked about yesterday. Again, not required, but if you're at all hesitant about the prereqs, especially the math prereqs, take that. It should give you a sense of what the second half is going to feel like. And yeah, so one new point, news since yesterday. The screen recording worked without any problems, which means that we're going to be posting screencasts for every lecture for the rest of the summer. Every morning before a lecture, that day's slides will be posted on edX on the syllabus, and every evening after a lecture, the screencast will be posted. So if you can't make it to lecture or want to watch at double speed or whatever else, that's now an option. Yeah, I just added this. I saw a lot of people had laptops out. Not a big deal, especially like don't bother moving today if you're wanting to take notes on your laptop and you're sitting in the front half. But just again, because some people are distracted by it if there's one in front of them, a screen, please, if you're planning on using your laptop during lecture, next lecture, sit in the back half of the room. Any questions about announcements logistics before we move on to actual material? Okay. So today we're talking about search, and a lot of what we're going to cover today is probably familiar from some intro to CS classes, although we're going to be presenting it in a different way than what you've probably seen before. First, I want to revisit this slide from yesterday. It's pretty important, and it's basically the framework that we'll be using for what is AI. And like we said yesterday, the course is about designing rational agents, and we define agents with this model. And so there are basically 6 or so things going on here. There are 2 pieces of our model: the environment, everything that is not the agent, and the agent. Where that line is drawn is, for a lot of the problems we'll be dealing with, pretty clear cut. When we're doing Pac-Man and the actions he can take, that's the agent. And all of where the dots are, where the walls are, where the ghosts are, all of that, that's the environment. And so the important things to keep in mind about this model are there are 2 ways that we interact with the environment. We get input, sensory input from the environment, percepts. In the case of this robot, the percepts are just what he can see, and maybe also if he has any other sensors about balance, where his joint angles are, anything like that. And then the actions are going to be all of the parts of this robot that it has total control over, like where is this wheel spinning, what are these arms doing, etc. What we're mostly dealing with is treating those as fixed things that we have no control over and figuring out what goes in this box right here, the algorithm that takes us from the sensory input that we get to the actions we want to take. In Pac-Man, the environment, like I said, is the board and all the dots and ghosts, everything that we have no control over. And the percept there is not as straightforward because we don't usually think of Pac-Man as seeing what's in front of him like we might with a robot. In fact, when we're doing Pac-Man problems, we're going to see the entire board and be able to see the entire configuration, just like when you're a human playing Pac-Man. And so the percept in that case is just the entire configuration of the board that we can see. And then the actions are north, south, east, west. We'll get into that a little bit more later. So today, we're talking about agents that plan ahead. And when I say plan ahead, as a human, we do that about everything. Anything we try to do, we're going to plan ahead, imagine what our actions would do. And in order to get computers that emulate human behavior in those situations, we have to explicitly code what it means to plan ahead. And so you should be thinking about having some internal model of how your environment works and imagining what the results of your actions would be in this internal model so that you can guess what will happen in your real world. Pac-Man's real world is a game of Pac-Man. So Pac-Man will be running a game of Pac-Man in his head to imagine what will happen, and then take a move in the real Pac-Man world. The way that we're going to approach this today is by modeling search problems. So a search problem is basically a general framework for solving a certain type of problem, where once you are able to frame your real-world problem you're trying to solve as a search problem, according to the definition we'll give pretty soon, any of the search algorithms that we cover today will get you a plan from your start to whatever goal you're trying to achieve. And the search methods we're going to cover today, the algorithms that will do that, are depth-first search, breadth-first search, probably familiar if you've taken CS61B or any data structures algorithms classes, and uniform cost search, which it's not written in here, but if it helps, it goes by another name, Dijkstra's algorithm. The presentation again today is probably going to be a little different from what you've seen before though, so we're going to stick with a different name. Again, if that helps with intuition at all though, it's related. Okay, so of course, talking about agents that plan, and it may seem natural that in order to solve a maze or any of these things, you do have to look ahead and imagine what the results of your actions would be. But for some AI environments, problems that you're trying to solve, it may not be the first thing that you think of. For example, suppose you're designing the software that's going to go in a Roomba, one of those little automatic vacuum cleaners that drives around on your floor and picks up stains and dirt and stuff. Well, assuming, for a simple example, that the Roomba can just see where dirt is, it's probably a good enough algorithm for that case to just say, see dirt, move in that direction, and then if I'm standing on dirt, clean up the dirt. That doesn't really involve any planning as much as what's in front of me right now, take an action right now. And we have a name for agents that work that way. They're called reflex agents. And so a reflex agent is going to choose an action based on the current percept. If you imagine that function, it's basically, well, yeah. Reflex agent doesn't plan ahead is probably the easiest definition to have in your mind. And it may have memory or a model of the world's current state, but it's not simulating the effects of its actions in that model. So remember the definition of rational we talked about yesterday? Optimal in the sense of having a goal, a utility that you're trying to maximize, and taking the correct actions to maximize that given what you know about your environment. So another word, when you see rational, think optimal, very similar in this context. So the question is, can a reflex agent be rational? I pose that to you, yes, no. Just shout it out, what you think. Yes? Yes. Okay, that's good. The important thing about rationality is that it means something different depending on what your environment is. If you remember, I talked about yesterday distinguishing between thinking rationally and behaving rationally. The definition of rational we're using only depends on how it acts. And so if you have a simple enough environment where you can get optimal behavior without simulating, then you will have a rational reflex agent. So here's an example of what that looks like. Pac-Man here, all he's going to do is say, where's the nearest dot? Take step in the direction of nearest dot. And that's all it takes. In this environment, that is plenty sufficient to get the best path he possibly could to eat all the dots. But, yeah, question?
Would that Pac-Man also be rational if it wasn't actually given like searching code that was just told turn right when you hit a wall? Or would that just be
in that case, an agent, there are lots of even simpler agents that would be rational there, like just go forward until you hit a wall. That tends to be the case in really simplistic environments like that. But here's one where the same agent doesn't do quite so well. Again, which direction is the nearest food pellet in? Move in that direction. Let's see what happens. Well, we already see it's missed a lot of things we know it should have done, but now it's happening. Yeah, exactly. I don't have my pointer for this, but the nearest food is 2 spaces to the right of it, to the east, and so it's moving east. But there's a wall there, so it's just smacking into the wall over and over and over. I wish we had that animated in the demo. That would be fun, but as far as we can see, it's just stuck there. So what we would need to fix this is to be able to look 4 steps into the future in this case and say, well, moving east is not going to end up getting me any closer to that dot, but if I go south, east, east, north, then I'll get the dot. And that's kind of the idea behind these search algorithms. Yeah?
Are reflex agents basically like 3D?
Yes. Reflex agents are greedy according to some, basically, you define a evaluation function, which in the case of this one is just how close am I to the nearest dot, and a reflex agent is going to greedily, so the most it can do in one step, minimize or maximize that evaluation function. And we'll talk about greedy algorithms more generally tomorrow. All right, I'm going to close that before that gets too negative and we get too sad. Okay. So, oh yeah, one more question. Okay. Definition of rational, just to recap really quickly, is you have a goal defined as a utility function. In other words, of all states you could possibly be in, you've ordered them which ones are better than others. In the case of Pac-Man, your utility function usually is just going to be your score. You want to maximize that. Rational agents are ones that take optimal moves in terms of maximizing the expected value of the utility. I say expected value because pretty soon we're going to get into environments where there are random events. Right now, we know exactly what the results will be, but pretty soon that won't be the case.
It's maximizing the expected, not necessarily the optimal.
It is maximizing the expectation. As far as we're concerned today, there's no randomness, so it's just maximizing the utility. And yeah, getting to a goal as quickly as possible. So planning agents. Here's how we fix that problem. They ask, what if? If I move south, what will the state of the game be? Will I be any closer to achieving my goals? That would be one step looking ahead. And so it's going to hypothetically imagine what these results will be and look as far ahead as it needs to actually determine a path to its goal. It must have a model, of course, otherwise it won't be able to simulate in its head what's going on, and it must have a clear concept of what a goal is. That reflex agent, it didn't have a clearly defined goal as much as just an action as a function of what it sees. What I mean by that will become clear when we talk about the formulation of a search problem. There are 2 questions that we want to ask about different search algorithms. The first one is optimal versus complete. Optimality means if there are multiple paths to a goal, are we going to find the best one possible? So in the case of Pac-Man trying to eat all the dots, your goal is to eat all the dots, and you want to do it in as few time steps as possible because your score is decreasing by 1 with every tick of the clock. And complete means if there exists any solution at all, will this algorithm find it? 2 good vocabulary words to know. And then planning versus replanning. These 2 demos we're going to see in a second will illustrate that. Planning is seeing all the way to the end, the path to your goal. Replanning is defining some intermediate goals that once you achieve all of them, you will get your bigger goal, and then just solving a bunch of smaller search problems. So we're going to see replanning first. So what this one's going to do is identify which dot is closest to it, and then make a plan to get from where it is to where that dot is. Okay, so it finished with a score of 907. I heard some skepticism there, and that's good because you may have noticed that there was a different path it could have taken that would have gotten a slightly higher score. Now, this other Pac-Man, who we've called Mastermind, he actually, rather than saying, I want to get to the next food pellet, how do I get there? He says, I want to get all of the food pellets as quickly as possible, looks all the way to the end of this trajectory, imagines every single sequence of actions it could take, and then figures out which path is the best. Now, of course, that's going to take a second. Searching for a path, doing some pre-computing, and now it's just trying a whole bunch of different trajectories. I think we'll get a printout of how many it's tried. There, it's done 1,000. Takes some time. This is not really a viable strategy for boards much bigger than this, for a reason you'll see. Yeah, one second. So first just watch, this time it went to the left, and it had a lot fewer steps where it was not eating food. And this, so we got 914 this time, as opposed to 907 from replanning. Not a huge difference, but the Mastermind Pac-Man was optimal, where the replanning one was not quite. Rational, equivalent terms in this case. So you were asking, wouldn't work for the competition?
Yeah, something like that would immediately lose your game since you have to wait a full 30 seconds.
Yeah. If the kind of environment you're working with is one that's not frozen while you think, one that is moving while you're deciding what move to make, like a robotics problem in the real world or something like that, then you can't spend a whole lot of time thinking in between every move. That won't quite work. And yeah, so throughout the semester, we'll see all sorts of different ways to address the speed problem as well. Question?
Is the 907 one not rational?
Yeah, so the 907 one is not rational in the technical sense.
Or the 914 one is rational?
Yes, and I haven't proved that to you, except by telling you that this is a search algorithm that will later prove is optimal, that just computed 914 is the best we can do.
What do you use to assess this? Do you use how much? In some ways, that wasn't really rational because it took such a long time. So if you were thinking about it as in how much time it takes, it might not be rational.
Yeah, good question. So the question is, it took so long, does that contradict it being rational? And the answer is, this particular environment, the way this game was set up, the score counter is not ticking while it's thinking. It's a little contrived. It's for the sake of the demo. If we were in an environment where things are going on even while Pac-Man's thinking, then that would not be able to achieve an optimal score. But in this case, our utility function is only the score at the end. It doesn't account for how long it takes to compute. Good question. Okay. So, search problems. I think an easy or a helpful intuition here, if you're familiar with coding in Java, is an interface. And I'll go through, you might see what I mean as we do this. I'll finish all of this and then go back over it with that in mind. But there are, a few parts of a search problem. The first thing it has to have is a state space. So in all the Pac-Man problems we'll be considering, it's just a set of all states that the environment could be in. There's an example. A successor function, and so that's something that says, oh, hang on, I want to show that, yeah. Given my current state and an action I want to take, what will the resulting state of the environment be? And here you can see we have in this state, if Pac-Man moves north, then it's going to go up 1, and then there will not be a dot there anymore. If it goes east, it'll be over 1, and there won't be a dot anymore. And for the environments we're considering, we also need to have a notion of cost, and we're trying to minimize the cost. It's a typical graph search way of viewing the problem. For Pac-Man, every step you take, your score goes down by 1. And so just every single action is going to have a score of 1.0. We'll see examples in a minute of problems where the costs actually vary with different actions. So that's the second piece of a search problem. And the last part is a start state and a goal test. Start state, pretty straightforward. It's which configuration of the environment are we starting in. A goal test is not as straightforward because it's not necessarily just one state. You could say, well, if the problem were I want to eat all the dots and have Pac-Man in the center of the board, then that's one state. But that's not usually the way we formulate this problem. We just want Pac-Man to eat all the dots, which means this state, or any other state where there are no dots left, regardless of where Pac-Man is a goal state. So a goal test can be something more general than just a list of states. It can be some function that you run on a state to determine whether or not you've completed your task. And then a solution, which is what these algorithms will return, is a sequence of actions, a plan, that transforms the start state to some goal state. What's important to remember is that search problems are just models, which means when you're trying to solve real-world problems with these, they generally will not be perfect. If you run into weird solutions that don't make sense in the context of your real-world problem, it's much more likely that there's an issue with the way you're modeling the problem than in one of the search algorithms. That said, when you're designing the model, you have to balance keeping all of the information that is relevant, important to actually solving your real-world problem, without capturing every piece of information about the environment if it's not relevant to the problem you're trying to solve, because if you do the latter, you usually end up with an intractable problem. And we'll see a Pac-Man example to make that concrete as well. But first, as promised, here's an example where different actions have different costs. Traveling in Romania. So here we are starting at Arad and trying to get to Bucharest. Our costs are how long it takes to drive along each road. Not necessarily the same as distance, because it's going to factor in other things like traffic and stoplights, all sorts of things. This is the way mapping software works. These are all the roads and how long it takes to drive along them. Determine the quickest path from Arad to Bucharest. So, what is the state space? In this case, the state space is cities, because all you need to keep track of to be able to solve this problem is which city are you currently in. And then the successor function is taking an action that is to go along one of these roads. So if you're in Arad and you take the action go to Sibiu, then the successor function will say, okay, now you're in Sibiu and you've incurred a cost of 140. The start state, like we said, is Arad, and here we have a very simple goal test. Is the state that you're currently at Bucharest? If so, you've solved the problem. So a solution here, like I said, a sequence of actions that take us from the start state to a goal state. Not guaranteeing an optimal solution here, not until later, but this would be an example of a solution in this case. The action to go from Arad to Sibiu, from Sibiu to Râmnicu Vâlcea, to Pitești to Bucharest. Any questions before we move on? Yeah.
For the state space, is it just the cities, would that include like the cities within, or just could you define it? Because when you say cities, I see all those cities.
Yeah. Good question. Define what I mean by cities a little more detailed. Okay. So the set of states is going to be this set. Arad, Zarind, etc. And for the sake of solving the problem we're trying to solve, getting from Arad to Bucharest, the only information we need to know is where we are right now. Even if we were previously in Bucharest or anything about the history where we were before, where we came from, that doesn't make any difference in what it takes to get from where we are now to Bucharest. And so this is the only information that we need to keep track of in a state, is what city we're currently in.
You also need to keep in mind the places you could go to. Because there's no way you can know the shortest route just by the cities next to you.
The cities you could go to?
Yeah.
Okay. Yeah, that's information that your agent will have to be able to solve this problem. But we don't normally put that in the state space. That's going to be information that's baked into the successor function. What I mean by that is the successor function, when you take a rod, what is the successor of a rod? When you take the names of the actions for this environment are a little weird. It's go from a rod to Sibiu. Then you'll end up at Sibiu. And so in order to simulate paths all the way to Bucharest, that's all you need to be able to do, because you just do that once for where you are. Imagine a future where you've taken that action on and are now at Sibiu, and do it again from there. Yeah? Cost is also going to be, yeah, as far as the information about how you incur costs, that's going to be in here. How we keep track of what costs we've incurred, that's going to be something done by the algorithm, which is a part of this that we haven't gotten to yet. Okay. So back to the question about how to model these problems. So what's in a state space? The world state includes every last detail of the environment. Search state only keeps what's relevant for planning. So if we're solving the problem of pathing, which means we're at the point x1, y1, and we want to get to the point x2, y2 in this maze, the states are going to be our current location. That's it. We don't need anything else. The actions are the directions we can move. And the successor function is, according to each action we take, where do we go next? And we don't need to keep track of what else is going on the board, because we don't care about what the pellets are doing. For the sake of the pathing problem, there are no ghosts. And the goal test is, are we at the target position that we had laid out before? Is current xy equal to the goal position? But in this same world state, if we're solving a different problem, like eat all the dots, again without ghosts, I probably should have used a different picture there, we need a little more information. We can't just know where we are now. We also have to know which food is left. It's also not enough to know how many food are left, because if I say Pac-Man is right here, and there are 30 pieces of food left, it makes a difference in terms of what plan Pac-Man is going to choose if those food are in this configuration, or if there are also food over here instead of over here, something like that. So the information we need to be keeping track of to solve this problem is, where is Pac-Man and where is there still food? Actions are the same, north, south, east, west. But in this case, the successor function, because the state is encoding where those food are, if you take a step into a new position where there is a piece of food, you have to change the Boolean saying there was food there from true to false. And then the goal test, in this case, again, we don't care about where Pac-Man is, just that all the food is eaten. So is our current state one in which all the food is eaten, all the dot Booleans are set to false? You'll get a bit of practice with this in Project 1, where you have to define a couple of different Pac-Man problems as search problems in this way. So state space sizes. Here's a strange board. We have ghosts over here that can't actually interact with Pac-Man. So they don't matter to us at all, but they are part of the world state. In this world, there are 120 places that Pac-Man could be over here. There are 30 different pieces of food, and so we need to keep track of, for each one of those, whether it's been eaten. There are 12 positions that these ghosts could be in, and Pac-Man could be facing north, south, east, or west. Now, you may be thinking, why does it matter which way he's facing? He can still step in any direction. That's exactly the point we're getting to. How many states, world states, are there? Well, that's still information encoded in the world, which direction Pac-Man's facing, because you can see it right there. He's facing north, and sometimes he won't be facing north. So there are going to be positions for every combination of an agent position, all of the different configurations of which food have been eaten, so that's 2 to the 30. And then there are 2 ghosts that could be in 12 positions, so 12 squared times 4. That's a big number. But if we're trying to solve the problem pathing that I laid out on the last slide, just get from point A to point B, what do we need to keep track of? Yeah, just XY location. Where the ghosts are doesn't matter. They can't do anything to us. Which food have been eaten doesn't matter. We're not trying to eat all the food. And which way we're facing doesn't matter, because no matter which way we're facing, we can still move in any direction. So it's actually only 120, a lot less than the number of world states. If we're considering the eat all dots problem, now how many search states are there? I think I'm hearing mumblings of the right ideas. We need to be keeping track now of where Pac-Man is. That's relevant to the eat all dots problem, and which food have been eaten. So we end up with a much bigger number, 120 times 2 to the 30, but still not the same as all of the world states, because there are a lot of world states that, for the sake of this problem, are the same. If Pac-Man is here, none of the food are eaten and the ghosts are here, exactly the same as if Pac-Man's here, none of the food are eaten and the ghosts are both at the top. So here's a quiz, kind of next level of this same problem. Here's a new search problem, which is safe passage. We want Pac-Man to be able to eat all of the dots while keeping the ghosts scared permanently, from beginning of execution to the end. So when Pac-Man eats a power pellet, the ghost stays scared for some number of time steps. And for the sake of this exercise, if Pac-Man and a ghost collide, say the ghost goes back to home and is still scared. So take about 30 seconds, talk to your neighbors, try to figure out what the state space for this is and how many states there are. You can go ahead and search it.
How long does a pellet keep scared?
It's just to be clear, you're not trying to look at the board and come up with a plan, but how we would model this as a search problem, what the states would be. All right. Yeah, I'll give a couple more seconds. People are still thinking. It doesn't matter. Just keep them scared. Okay, let's bring it back in. So raise hands, I'll go around, ask some ideas about things that we need to keep track of in this state space. Yeah, go ahead. Yeah.
Steps to the closest power pellet.
Steps to the closest pellet? To the closest power pellet?
Yeah.
Okay. All right, what else? Yeah. How much longer the ghosts are scared? Ghost scared time. What else? Yeah. Where the ghosts are, okay. What about the more mundane things? Pellets, okay. Which pellets? What was that? Food and power. Location of Pac-Man. I think food and power is steps to closest pellet and where ghosts are. Or we can also add up here where are pellets. Okay. Yeah.
I have a question. Did you say that when he hits a ghost, then that ghost will get scared?
If he hits a ghost that is scared, then it stays scared. It will go back to home like in normal Pac-Man, but stay scared.
So he's not safe all the time.
Right. Only if the ghosts are scared. Yeah.
So then we don't actually need to know where the ghosts are.
Yeah, that's a good point. So, turns out that we don't need to know where the ghosts are, because if they're scared for the entire execution of the problem, then it doesn't matter to Pac-Man where they are. He can collide with them or not, and it doesn't change whether or not a certain path will take him to a goal state, eating all the ghosts. If we're concerned about that in the first place, that means that the ghosts have become unscared, and we've already failed to solve the problem. So we don't need to know where the ghosts are, but we do need to keep track of how long they're still scared. And we need to know where Pac-Man is, like before, since we're trying to eat all the dots, where all of them are. And I changed this to where are pellets, because if you know where they are, then you know how many steps there are to the nearest one. And it's not quite enough just to know the number of steps. You need to know where they are so you can plan far ahead. Yeah, question?
I actually advise you would need to know the ghosts are to start off with. Because if we're
Okay, fair point. I should have said, say they start out scared for one step, and it looks like this. Yeah, sorry about that. But supposing you can scare them on the first time step and then keep them scared is the goal. Then that's that. Okay. So agent position, dot booleans, power pellet booleans, and remaining scared time. Yeah.
So, like, with the wall, how would it, because in the previous example where we're bumping into the wall,
Mm-hmm.
how would the wall fit in and like intimate those into the workspace?
Yeah, great question. It's where do the positions of the walls fit into this? And like before, they're not going to go into the state space. That's going to be another thing that's in the successor function. Because if Pac-Man is right here, we have a successor function that says the result of moving south is that you don't move at all. So since the positions of the walls are not going to change throughout execution, that doesn't need to be a part of our state space. Just tracking it in the, or having the successor function encode that information is enough. So now we're going to start getting into the model that we use in order to run our search algorithms. So a bit lower level than just specifying the problem. A state space graph is a mathematical representation of a search problem. Looks kind of like this. So this is not the full state space graph. The full state space graph is much bigger than this. But you can see we have a start state right here. And then every action that you can take from that state is an arrow coming out of that will lead you to the successor state. And in this graph, if you're here and you move down, then you're now here. If you're here and you move left, you're here. So there can be cycles. If you end up at the same state again, there's going to be one node that represents that, regardless of the history of how you got there. This is not really a sensible way to implement in code. Generally, this graph is going to be way too big to fit the entire thing into memory at any point in time, but it's a really useful way of mathematically reasoning about these. Most of our algorithms are going to, in some sense, partially build up this graph and the state space tree, the next thing we'll look at, in order to determine where it wants to go. Not the whole thing, but just a piece of this. That's an important point. The goal test is a set of goal nodes. So I mentioned those other 2 points, but in this graph, there are going to be 9 different states somewhere in here where there are no food pellets left on the board. And so the goal test is Pac-Man in one of those states in this graph? In a state space graph, each state occurs only once, like I said. There's this cycle here because if you ever end up back somewhere you've already been, then you're back at a state in the graph where you've already been. And we can't build it in memory. A lot of our examples are going to look like this, where they don't really correspond to any real-world problem we're trying to solve, and they're very small, just a few states. But seeing and intuitively understanding how these algorithms run on the small examples will help you understand how they run on real problems like Pac-Man. Yeah. So here's another concept, search trees. And the difference here is now, basically the main difference is that if we end up at another state, at a state we've already been at before, that's its own different node in this tree. So we start out with just the start state at the root of the tree, and then one action, one step into the future, shows us the second level of the tree. These are the actions that we can take from that state and their costs. And each of these will branch into all of their possible successors. The big important difference that helps us algorithmically with thinking about search trees is that now, since there's a different node in the tree for every path to a particular state in the game, the nodes here intrinsically encode a path to get from the root, the start state, to that position, that board configuration. So if we have a node down here that's a goal node, that's a goal state, it'll show something like Pac-Man's in a board with no food, and then by following that back up to the root, we'll have gotten a plan, a solution to the problem. Yeah?
For simulations like that, there's a whole lot of different ways to get the optimal path 8 moves. So how would it calculate between the best of the same answers?
Yeah, for the purposes of this class, if any 2 answers give you the same utility, are worth the same, then we're just agnostic to which one you pick. You can just choose arbitrarily among them, and that's optimal. And in fact, that's quick terminology point. Optimum means that there's one that is optimum. Optimal means that it has the property of being not worse than any other. So yeah, finding an optimal solution, any of them that is not beaten by any other solution is fine. So like I said, the difference here, main difference, is in the search tree, the same state is going to appear in several different nodes. That distinction I'm making between state and nodes might be a little bit hazy at this point, but we have a lot of homework problems on it. And so that will become clear if it's not already. And in both cases, we're going to construct them on demand, only the part of it that we're currently looking at. Try to store as little of it in memory at once as possible. Notice that over here in the search tree, there are 2 Gs, and this just happens to be the one that is in red, actually. We haven't run an algorithm on it, so it's just the one that's in red right now. Yes?
So why do you want to do a search tree?
The reason that we'll want to do a search tree is something that we'll be talking about for today and tomorrow. Basically, tree search algorithms, which we'll cover today, work with search trees and graph search algorithms, which we'll cover tomorrow, work with graphs. And so as we cover those, the differences and their strengths will become clear. So 4-state graph, quick quiz. You can just shout it out. How big is the search tree for this graph? Was that? Infinite. Yeah. And if you don't catch that right away, what's happening is we have a cycle here, right? And so if we start at S, then we have A and B, and a successor of A is B. There's some other stuff too, but there's a B here, and there's a successor of B that is A, and on forever. So we have an infinitely large search tree. Unfortunately, I don't have an eraser on this tool, so there's that. So there's a lot of repeated structure in the search tree. We'll see this come up again and again today and tomorrow. So the first 3 algorithms are tree search algorithms. The example we'll keep in mind, again, is finding a path in Romania, getting from Arad to Bucharest as quickly as possible. This is what the search tree for that problem looks like. Our start state is Arad, so that's the root of the tree. And then all the successors are the first layer, successors of those are the second layer, and on and on. So the general idea of one of these algorithms is expand out potential paths, potential plans, which are the tree nodes. Oh. Okay. And maintain a list, a fringe of the partial plans under consideration. Remember that since this is a search tree, we're not just keeping track of which state we're at. This node in this tree has our current state, Arad, but also because we can follow it back up to the root, it has the path we took to get there. And then, again, trying to do this quickly and without taking up too much memory, we attempt to expand as few tree nodes as possible. Hopefully, when you do this, you find a goal long before you expand the entire tree. So here's the pseudocode of the general tree search algorithm. And the 3 algorithms that we'll be covering today are just specific implementations of this general algorithm. So it takes in a problem, which, again, a search problem is one of those objects which has a state space, a successor function, a start state, and a goal test. That's right here. And then a strategy. Strategy is just, are we going to do depth first, breadth search, or uniform cost? Breadth first or uniform cost. We initialize the search tree using the initial state of problem. That's like what we did back here with just Arad at the beginning. Oh no, I won't do that again. And then we loop. Like I said, expand something that is some plan that's currently under consideration to consider all of its successors. And then if that state that you've just found is a goal, return the path that you took to get there. Otherwise, add all of its successors to that list, that fringe that you're considering. And that's actually the entire algorithm. So that leaves us with a couple of questions. Well, one main question really, which fringe node to explore? So this, choose a leaf node for expansion according to strategy, there's a good bit of abstraction there, and that's what the rest of this lecture is about. The order that we choose the leaf nodes is going to make a big difference in how this algorithm plays out. So as a quick example, I'm going to run through I'm choosing arbitrarily, not according to some strategy, the order that will expand these nodes. So the start state here is going to be S. And then, actually, let me do this. I'll draw the tree here, S. And then the fringe over here starts out with just S. We're in that loop. We take something out of the fringe. Right now there's only one thing. And look at its, check if it's a goal. It's not. Look at its successors. So those are D, E, and P. And so we're going to add these to the search tree. And our fringe is going to contain these nodes. And now, pick something from that fringe, remove it. I will pick E. Now, we're going to expand E. Is it a goal state? It's not. So we add its successors to the fringe. SEH, SER. And then we're going to continue like that, checking every time if it's a goal state until we get there. This search algorithm is called I already know the answer. So I'm going to expand R next. And then we're going to get SER removed from the fringe, SERF, and expand F. It's not a goal. Add its children. And so we have C, G. I see that's getting kind of hard to read. But now we have S, E, R, F, G. And then S, E, R, F, C. Pick something off of the fringe to expand. This one, is it a goal? It is. So we return this path. You're going to be doing this by hand a few times on the homework, but that's just a quick run through of what that looks like. Yeah.
But how would you actually get the computer to choose E first?
That's what we're going to cover for the rest of the lecture. The computer doesn't have access to the I already know the answer algorithm that I just used. But what it does have is depth-first search. And so the depth-first strategy is to expand the deepest node currently in your tree. What that looks like on this tree is this. So first, of course, you start out only your roots in there. Now you have 3 things in there that are all equally deep in the tree. They're at this level. And so we'll just break ties alphabetically. We'll expand D. And then, sorry, I'll step back one. Oh, jeez. Now our fringe rather, contains B, C, E down here, and then E and P. These 3 are deeper. So we're going to expand them before these ones. Break ties alphabetically. Again, B. B. Now A is the deepest one. Expand that. A has no successors, so that doesn't add anything to the fringe. Now the deepest thing on here is C and E. Alphabetical ties. C goes to A. And then deepest thing left is E. And you can see we're kind of doing a left to right sweep across here when we've organized it alphabetically. We're just always choosing the deepest thing in the tree. So the reason we say that it's a LIFO stack, when you're actually implementing this in code, a fast way to do it is rather than actually check the depth of each node and implement this as a priority queue where you just take out the deepest one, if you say the last thing that I added to the fringe is the first thing that I'll take out, then that will end up giving you this behavior. Because the last thing that you put into the fringe, since you previously expanded what was already the deepest, you added nodes to it that were one step deeper than that. So they must now be the deepest. And yeah, so we end up, I can't take one step back. I have to clear the whole slide. Nice slide. Okay. So, yeah, quick question. Yeah, we'll see cases where it's good and where it's bad. Yeah.
And for that first tree you showed us, the infinite loop, wouldn't that potentially just crash the computer?
Yes, and that's actually the answer to this question. Is this algorithm complete? Well, if you have a finite search tree, which you don't have if you have any loops in your problem, then yes, it's going to eventually search that entire tree with that left to right sweep. But if you have somewhere on the left side of that tree, before you find a goal, like we had in that AB example where it went down infinitely deep, then you can get stuck there and never actually find a goal. So it's complete for finite search trees. Is it optimal? No, right. Because it's only going to find the first solution it sees, the leftmost, regardless of how deep it is in that tree. Time complexity. Well, in the worst case, if your tree looks like this, and your only goal is over here, it's going to search that entire tree. So in the worst case, the time complexity is the size of the search tree, the number of nodes in there. And, whoa, oh no. Hang on. This is not going to fly. Okay. So the time complexity is going to be your branching factor, which is the number of actions you can take at any step, the number of successors you might add, raised to the power of the depth, because that's roughly the number of elements in the tree. And space complexity we'll address in a minute when we have this useful picture. One thing about this, we're going to be using this a bit to visualize these. Keep in mind that it looks like on here, as you get deeper, the width of the tree is increasing linearly. It's actually being multiplied by your branching factor each time. So it's a little misleading. This should be growing out exponentially wide. B is the branching factor. So in the first row we have 1, then B squared. And we'll call M the maximum depth. So the lowest row has B to the M nodes. And there will be solutions at various depths. So what we mean by this is, this could be some state in the search tree that found us a path from Arad to Bucharest, went all over the place because you're all the way down here. And this could be another path that's a bit more direct over here. Number of nodes in the entire tree. Well, if we're exactly counting, then it's actually going to be the sum of all of these, 1 plus B squared, all the way on. But that's just O of B to the M. And so as far as analyzing runtime complexity and space complexity, as far as we're concerned, it's O of B to the M. So here's an animation of sweeping left across the tree. And if it's the worst case where our only goal is over here, it could process the whole tree. And if M is finite, then in that worst case, it will get O of B to the M. How much space does the fringe take? This is a little bit harder to visualize, but consider that when we start out, we just have this, and then we go down one branch of this, and when we're here, we expand this node's children, and maybe when we're done exploring everything over here, we're now exploring this branch's children, and we're going to have basically at each level, in the worst case, when we're all the way at the bottom, B different nodes. At each juncture, all of the different actions we could have taken, we're still exploring one branch all the way down to the bottom. And so it looks like this. Each of those having B elements in it, B nodes. And so the total number of nodes on the fringe, in the worst case, is O of B times M, the space complexity. Not bad. Compared to this exponential runtime, it's only, well, polynomial, much smaller, B times M. Is it complete? We already addressed this question. If there are cycles, then it could get stuck in them and not find a solution. Is it optimal? No. So next one we're considering is breadth first. Here we're expanding the shallowest node first. And unlike, or basically opposite of the depth first searching, in breadth first, it's first in, first out queue. We usually just call that a queue in data structure terms, which means whichever node has been in there the longest is the first one we take out. And that's going to give us this expand the shallowest node behavior. So this is what that looks like in the search tree. We have S. We expand S. Break ties alphabetically, we'll get D. And now the shallowest nodes in there are E and P. And so we'll go through like that. Now we've explored all of that second level. We'll move on to the third level. And we're just going to go across in level order like this, searching the tree. Now we want to address those same questions about BFS, because we're comparing these two algorithms to decide when each one is good. So, like we said, it's going to explore in level order across the tree. So that animation from last time here looks kind of like that, just going in straight lines down. And that means that it's going to process all nodes that are above the shallowest solution. So when I say shallow, I mean ignoring the actual costs along each edge, just the number of edges you have to traverse to get from here to here. That depth is S. Everything above S will process it. And so now we're dealing with the number of nodes we've looked at is the sum of all of these. 1 plus b squared, all the way to b to the s. O of b to the s. How much space does the fringe take? Well, in this case, our fringe can take up the entire width of whichever level of the tree we're currently searching. In the worst case, the only solutions are going to be all the way at the bottom. And so we will have the entire bottom row. Or more generally, just wherever the first solution we find is, that depth s, we'll have b to the s different nodes in the fringe. So that's the space complexity. Is it complete? Well, in order for s to be defined, if there's a solution at all, it has to be at some finite depth. So we will find it. It is complete. Is it optimal?
Well, it's kind of fast the solution first, not the solution.
Yeah. Okay. So I hear a lot of yeses, and it's a little bit of a tricky answer. If all of the costs are the same, then it's optimal, because it's going to find us the solution that takes the fewest number of steps. Breadth first search is not yet considering the costs on those actions, and that's the next algorithm we'll look at. Is it optimal? Only if all costs are 1, or if all costs are some constant. So now we have a quiz. DFS versus BFS. We're running, oh, actually we're not doing so bad. So take a few seconds to talk amongst yourselves about these two questions. BFS versus DFS, DFS versus BFS. What are their advantages? When would you want to use one or the other? And talk with your neighbors.
It's a long line. So if you're both doing the same breadth, but one of them that should walk the other that's correct. And the fastest, the shortest number of states.
All right, I want to bring it back in. So let's first get some ideas of when will BFS outperform DFS. Raise hands. Yeah.
If it's close to the right side, but not close to the bottom edge.
Okay. So if we're drawing this tree again, like this, that's if we have goals that are on the right side and not at the bottom.
Yeah.
So like in this region.
Yeah.
Okay. Yeah.
Maybe best for you.
Yeah, if we are, for these tree search algorithms where we can get stuck in these loops, breadth first search is complete. That's one guarantee we already have. So if there's a loop, we're safe from that in breadth first search. Okay, any other answers? What about what we said about the optimality of breadth first search? If we care about getting shallow goals, so in that case where the costs are all the same, we're just trying to get the fewest number of actions to get to a goal, breadth first search will give us the answer we want, where depth first search would not. Care about shallow goals. And another answer to that, which I guess is maybe just a slight generalization of what Zach said, is in general, if we have an environment where we know it's possible to go really deep in this tree, so this tree is this big, but we know there exists some solution at this level of depth, don't know where it is, but it's somewhere in there, then breadth first search is likely to get us there a lot faster than depth first search will. What about depth first search? You see a hand over there?
So perhaps with a limited memory because DFS takes significantly less memory than DFS does.
Yeah, exactly. That's one of the biggest ones is limited memory. Depth first search, remember, is O of branching factor times depth, where depth first search is that, where breadth first search is exponential in the depth of the shallowest node. So this is a lot better. What about thinking about the shape of this tree again? What kinds of trees would depth first search handle better? Yeah. Okay. Yeah. So now in this case, if we have solutions over here, usually we don't know where the solution is in advance, whether it's on the left or the right, but there are some environments where we can know. Like up here, we knew that there were shallow solutions. There are some environments where we might know in advance that the solutions are all somewhere at the bottom of the tree. We'll see some examples of this actually later this week when we talk about CSPs. Search problems where all of the solutions are somewhere on the bottom. And so we use techniques derived from depth first search instead of breadth first search. Yeah?
Does it really matter if it's on the left side or on the bottom or it's on the right side? Well, not the right side, but like in the middle. Because in that case, is that alphabetically? What is considered then?
Yeah. Yeah, right. If the solutions are at the bottom, then it doesn't matter where they are there. And actually this notion of being at the left or right depends on your tie-breaking strategy, which is not really something we usually think about that much. So we're usually more concerned with what depth the solutions are at, and where it is left or right, we treat as more or less arbitrary. Oh, okay. All right, great. So now we're going to see two examples of depth first search and breadth first search solving one problem. And shout it out when you know which of these is being run. So in this environment, we start at the green square, want to find a path to the red square, and whenever a state is expanded, we're going to see a dot pop up on that square. So just shout it out when you know, is this depth first or breadth first search? Oh, jeez. I have to be able to see it. That's important. Okay. Breadth first search, great. Okay. What about, well, you know the answer, but it's fun how depth first search handles this. There we go. Found a solution. So here's one where breadth first search clearly did a better job, or at least assuming that we care about the length of that path. Breadth first search clearly did a better job. Even if we don't, it found it faster, so that's better too. Let's bring this back up. Now, a question you might have, probably do have this question, I think this might have been mentioned in CS61B. Is there a way that we can put these two algorithms together, get the benefits of both of them without the disadvantages? And that's called iterative deepening. We get depth first search's space advantage with breadth first search's search order. And so the search order is what determines the time complexity and the fact that you get shallow solutions. And space advantage is DFS's main appeal. So the way this works is we say first, run a depth first search on the subtree of depth 1. So a subtree of depth 1, that's just the root node. And then if there's no solution, or sorry, depth 0 is the root node, depth 1 is all of these. If there's no solution, then start over, but this time run a depth first search with a depth limit of 2. If there's no solution, do it with a depth limit of 3. And we keep expanding our search horizon like this, running depth first searches. So isn't that wastefully redundant? Maybe your question, because we're searching the same nodes over and over and over again. But it turns out, remember, in the worst case, which is we fail the search, depth first search is going to visit each node in the subtree once. And so we end up with a search with one node, and then with O of B nodes in this bigger tree, O of B squared, on, until we get to the shallowest solution, O of BS. What's the sum of all of those? Well, it's still O of B to the S. It's actually still the same runtime complexity. The same time complexity as breadth first search. An intuition for what just happened there is almost all of the searching takes place in that last one. And next to the amount of searching that takes place, depth first searching the tree to the right depth, everything you did before that is almost trivial. So, quick recap of what happened here. The reason it's better, you can see that we're going to expand nodes in the same order as depth first search, but we're actually running, when we're looking just at this subtree, we're running depth first search, and so our frontier might look like this. That's still going to be O of BS in the worst case, space complexity. Because once we've expanded all the way down to S, we're going to finish. And we search that tree with depth first search, BS. Quick questions about that before we get to this last algorithm. No? Okay. Yeah.
You definitely not want to use that approach if you don't have memory problems. You just do DFS.
Tomorrow, we're going to see a different version of DFS that has some advantages that you can't get with iterative deepening. And so, as far as the algorithms we've seen today, iterative deepening is more or less strictly better than breadth first search. But we're going to see an improvement of breadth first search tomorrow that makes that not true anymore. Good question. Now, the next class of algorithms we're going to look at, breadth first search was optimal if we just want shallow goals, but now we're considering different costs on each edge. We want to find the path from start to goal that accumulates the lowest sum of the costs along that path. The algorithm we'll use, uniform cost search. Slightly unfortunately named because of the algorithms today, it's the one that is specifically designed for the case when you don't have uniform costs. But that's what everyone calls it, and so to be consistent, that's the name we're going to use. Back to this slide again, but now, see we have costs on the edges. So it's going to be a priority queue where when we choose which node we're going to expand off of the fringe, it's not based on its depth in the tree, but the cumulative cost to get from the root to that node on the fringe. So here's what that looks like visually. When we expand S Of course, that comes off first because the cost to get from S to S is 0. And now our fringe has S to D, S to E, S to P. Here, more than ever, the fact that our fringe contains a path to a node is very important because, well, now we're going to expand in order of cumulative cost. We expand P. On this graph, that's S to P, and now S to P to Q, that's what's right here. Notice that the cost is 16, which is this 1 plus this 15. So now the cheapest thing on there is S to D, and then to B from there, E, and it's not as easy just at a glance to draw what order it's going in, where with depth first search we had it sweeping from left to right, and with breadth first we had sweeping from top to bottom. But if you look at it with the numbers there, with this representation, it's pretty easy. Just go where the number is lowest. And to remind you, if you're wondering where these numbers are coming from, this S, D, E, R, F, it has an 8 because the path to go from S to D to E to R to F, that's 3 plus 2 plus 2 plus 1, 8. Then we expand that, then E is the lowest, then G, and we found our goal. So if you want to have a drawing of what the tree looks like, in this case, the order we expanded the nodes, it's a bit weirder. Looks kind of like that. And it is still, in some sense, a level order expansion of these nodes, except now instead of being all nodes that are at the same depth in the tree, it's all nodes that are at an iso contour. In other words, have the same amount of total cumulative cost to get to them. And so you'll notice the shape is going to be a little weird of these, but we still have, this is the first layer, then the second layer, third layer, fourth layer, etc. And that notion, tomorrow we're going to see a couple proofs that rely on a more formal view of what I just said. Looking at this again, what nodes does UCS expand? Well, it's going to look kind of like that. Now, so we're saying this is a deeper node, but that has a cheaper cost to get all the way to it. It processes all nodes with cost less than the cheapest solution. If that solution is C star, so C star is the cumulative cost to get from B to there, and the minimum cost of any one step along this path is epsilon, then of course the number of steps to get from here to here, where the minimum one is epsilon, is C star over epsilon. And so that's what we're going to call the effective depth, and that's how we're going to measure runtime and space complexity. It's going to be O of C star to the E, the effective depth, C star over epsilon, sorry. And the space, remember, it's still going to be working similarly to breadth first search, but instead of everything that is at the same depth, it's everything that is at the same cost. And so in the worst case, that's going to be everything that's at the same effective depth, C star over epsilon, O of B to effective depth. Is it complete? Yes? No? Yes. Okay. I didn't mention this, but it's a good call. Assuming there's a solution with finite cost and that all of your edges are positive, then the algorithm's complete. If you've seen Dijkstra's algorithm before, that's a big deal that you don't have negative edges. We are dealing with problems here mostly where all of our costs are going to be positive. If you have negative costs, then these algorithms aren't going to work. So right now we're dealing with things that this will actually work for. Is it optimal? Yeah. It's the only optimal algorithm we've seen today, at least in terms of edge costs. This is the algorithm that will find you the first. It's expanding things in order of the cost to get to them, and it returns the first one it finds. So it can't possibly find you a solution that has cost 10 if there exists one with 8, because it would have already expanded that one. We'll see a more formal proof of that tomorrow as a special case of the proof of the optimality of another search algorithm called A*. But for now, we're going to move along. So actually looking forward to tomorrow's lecture when we talk about A*. That's an algorithm that you encode some information in it about where the solution is, so it expands smartly, decides which direction to go. UCS does not do that. It will find you an optimal solution, but it explores in every direction without any information about the environment. So quickly before you go, I want to do one more which algorithm is which. So let's see that. Actually, to illustrate, oh no. Is that not working? Okay. Yeah. All right, which algorithm is this one? Breadth first, good. Yeah, it's just expanding everything that's at the same distance from the start state. All right, what about, I keep having to drag it over. What about this one? UCS, yeah, this is a uniform cost search. And the way you can tell is once that path over there got to the deeper water, I guess I should have mentioned, you may have inferred, deeper water is harder to trudge through, the more blue stuff. It expanded along the cheaper route first. It ended up finding a solution that is not the shortest distance, but if we have more cost along the darker water, it is the optimal solution. And then, of course, our old friend, depth first search, which looks like this. Okay, thank you. That's everything for today.